Hi. So I want to talk about growth of functions, want to talk about big O. So let's get started. I want to begin by talking about the motivation for the definition because really that's about half the job. So obviously what we intend to do is compare the performance of algorithms because typically you want to pick the best one. You know, you have a choice between a bubble sort or quick sort or this kind of stuff. And for our purposes, we are imagining that the input comes in some size, and then we're going to look at the resources that the algorithm uses, and almost all the time we'll look at the runtime that the algorithm uses. So sometimes other things, but much of the time the runtime. And the sort of mathematical idea there is there's a function that takes the input size and then outputs the runtime. And we want to compare those functions for example, for bubble sort or quicksort. Okay, so the tool that we're going to use to compare those functions is called Big O, and I anticipate that most folks are maybe not best friends with Big O, but at least reasonably conversant with Big O, or have some interaction with Big O already. If you haven't, that's fine. This is a self-contained presentation, but nonetheless, typically people have seen it already. Okay, so let's start by comparing two functions that are especially important functions, and that will give me some motivation for what I'm going to do. So I want to look at, here are the numbers 0 through 9, and this is their binary for the numbers 0 through 9. And down here is how many bits are taken up by the binary expression. Now 0 is kind of a special case, but the other ones are pretty straightforward here. So for example, 5 takes 3 bits, 8 takes 4 bits, this kind of stuff. The next line, I have the log base 2 of the number. Remember that what the log base 2 is, it's the power of 2 that equals n. So for example, the power of 2 that equals 8 is 3 because 2 to the third equals 8. And I only did it to 2 decimal places because it's good enough for our purposes. A person can see by comparing these two lines that the number of bits is simply you take the floor of the log base 2, in other words, you drop any decimal places, and then you add 1. Except for 0, which as I mentioned is already a special case. Okay, so here's a graph that compares the log base 2 with the formula that I just talked about. And the bits there is in bold, in blue, and the log base 2 function is in purple. And look at them, I mean, they're the same. Of course, they're not exactly equal. Of course, there's some differences. But for all practical purposes, those are basically the same function. So a reasonable summary of this graph is that the function giving the number of bits required to express a number n is the base 2 logarithm of n. And you can leave the fine points off. The +1 doesn't really make much difference, and the floor doesn't really make much difference. Really, the two are basically the same. Okay, that's the idea. We want to define the exact tool that we're going to use, the Big O, and to define it, motivation is sort of half the job. I need 2 points. The first point is going to be pretty straightforward, and the second point a little bit more subtle. So for the first point here, it's that we want to focus on the long-run behavior of a function. And so I have an example that shows that you have to be a little careful with short-run versus long-run for the kinds of functions that we're looking at. So I imagine that I have an algorithm that runs in time square root of n, and I have another algorithm that runs in time 10 times log base 2 of n. And looking at the graph there, you might say to yourself, well, I want the faster one. I want the one that runs in time square root of n, because square root of n is a smaller amount of time than 10 log n. You could say, done, let's go home. But it's not that simple. Because when you look at, when you look at just 0 to 1,000, when you look at 0 to 1,000,000, you get exactly the opposite story. That is to say, at some point early on, it becomes the case that 10 log base 2 of n is much faster than square root of n. 10 log base 2 of n is much smaller than square root of n. That is to say, you have to pay attention to what happens when n goes to infinity. You have to pay attention to the long-run behavior of these functions. So a point, maybe not the world's hardest point, but a point. Second point is a little more subtle. I want to compare these two functions. It's 1, 2, 3, 4, 5 numbers. It's nothing that took me a long time to cook up. but you'll notice that this person here, this function here, begins with 2n squared, and this function begins with n squared. When I ask the computer for the values from 0 to 20 and the values from 0 to 20, and then I plotted them. And a person sees, of course, that we already learned the lesson that you have to ignore this beginning stuff. That they might be in not the true relationship at the very beginning, but eventually you'll see that the long run behavior is for g of n to be above f of n, for g of n to be above f of n. So the first thing your eye sees is that g is bigger than f. But don't let your eye be fooled. It's true g is bigger than f, but when you look at what happens in ratio, because that's how you compare things, you compare them in ratio very often, when you look at what happens in ratio, is that basically g is twice f. That is to say, g is ahead of f, that's true, but g is maintaining a kind of a steady lead of being twice f. There's some initial fooling around, but pretty soon g is basically twice f, and a person sees right away why that is, because up here in the expression for g, the dominant term is 2n squared, and in the expression for f, the dominant term is n squared, and 2n squared is twice n squared. And this other stuff makes it be not exactly equal to 2, but basically g is twice f. Okay, so I'm comparing that example to the next example. I went in and I changed g from 2n squared to 2n cubed, and I did the same thing. I asked the computer to show me the values from 0 to 20, and look at the difference here between the prior graph and this. Look at g is not just a little ahead of f. G has zoomed ahead of f, and g is racing ahead of f, and I can make that mathematically precise. Whereas before, g was maintaining a steady lead of twice f. Here, g is first g is 10 times as big as f, then g is 20 times as big as f, then g is 30 times as big as f. G is accelerating away from f. Bye-bye. It's gone. Okay, so I want to capture those 2 points. I want to say that we consider functions in their long-run behavior. That's the first point. And second, we consider functions comparable when the ratio g over f is a constant value, but we consider that g is sort of genuinely ahead if the ratio is increasing. Okay, so here's the official definition. So first point is that it might be most natural to think that, well, computers take in bits and put out bits, and so you might say, well, so we're working entirely discretely, so we should work with natural numbers. But that proves not to be right. It proves that experience with the subject is that you're often interested in things like the base 2 logarithm, which most naturally takes in as input real numbers and puts out as output real numbers. And in fact, the base 2 logarithm isn't even defined on some inputs. So we'll adjust the definition to instead, f and g are functions that input and output real numbers. And then we'll say f is big O of g, and you read that out loud as f is big O of g, when there are constants capital N and capital C, so that anytime x is greater than capital N, that is from some point on, anytime x is greater than capital N, then f and g are defined on x, so we get rid of this not defined on zero nonsense. F and g are defined on x, and furthermore, c times g is greater than or equal to f. So if you have one function that's a half of another, all you got to do is multiply it by 3, and now it's above. So this business of being like half or a third, that goes away. We're considering that to be a wash. Now, accelerating away is a different story entirely, but we're considering a constant multiple to be a wash. I have a comment about the notation. I prefer f as big O of g. I'd like you to prefer it too. But you'll often see people say f is an element of big O of g. That's perfectly fair. You very often also see this. You would read that out loud as f is big O of g, but the equal sign isn't the regular equal sign that a person learned in high school, calculus class, for that matter, in grade school. It's really the word is. So although it's standard, it's really very awkward, and it would be better if, given the choice, if you omitted it. I prefer to do what's in red. You can do what's down here, but please, if you have the opportunity, omit that. If you see it from somebody else, you got to know what they're talking about. But when you're writing on your own, it's better to do other things. Okay, so time for some examples. 3 examples, and then we're eventually going to show you a shortcut. But first, I have to show you examples that illustrate the definition. Okay, so here's a simple example. F is x squared, g is x to the fourth. And we have the sense that x squared is somehow a smaller sized function than x to the fourth, and that's what we want to show. We want to show that f is big O of g. So in order to show that, the definition requires that we produce a suitable capital N and capital C, and then go on to verify that they work. So I picked capital N is 2 and capital C is 1. And then the verification goes, anytime the input to the function is greater than capital N is greater than 2, then capital C times x to the fourth, capital C is 1, so capital C times x to the fourth is obviously x times x times x. But if x is greater than 2, then x times x is greater than or equal to 4. So we get 4x squared, and of course that's the x to the fourth is greater than or equal to 4x squared is all I need, because I have I have x to the fourth greater than 1/4 x to the fourth is greater than x squared. Okay, so let's try another one. We have f of x is 2x cubed and g of x is x cubed. So we have the sense that these two, that there's a greater than or equal to relationship. In fact, we have the sense it's an equal to. But anyway, we have the sense that there's a greater than or equal to relationship. I want to verify that f is big O of g. So I'm going to pick a capital N to be 0 and capital C to be 3. Then the verification goes, if x is greater than or equal to 0, then capital C times g is 3 times g is 3x cubed, which is greater than 2x cubed. And that's, so C times g is indeed greater than or equal to f. All right, so even though g is smaller in the sense that it's less than or equal to, the values are less than or equal to. In fact, we can multiply g by some suitable number and make the values greater than. There's no kind of accelerating away situation here. We will soon enough see, I'm going to call it a shortcut to do these two, soon enough. But I wanted to do an example once I had some practice. I wanted to do an example where the shortcut we're going to do, I'm going to show you, wouldn't work. So this is one reason why we show you the full definition, is because in some cases you need the full definition. All right, so I'm looking at f of n is n factorial and g of n is n to the n. I'm going to verify that f is big O of g, take capital N to be 1 and capital C to be 1, and then I have to do the verification. If x is greater than or equal to 1, then we have that capital C times g of n, which is n to the n, and that's n many n's, is greater than or equal to, there are n many numbers over here, but most of them are less than n. 1 is less than n, 2 is less than n, etc., and that's f of n. Okay, so here, the shortcut I'm going to show you involves some kind of calculus calculation. It has L'Hopital's rule, in fact, in the mix, and we don't know how to do calculus on things like the factorial function. So we would have to apply the definition as given. Okay, a couple of lemmas, couple of intermediate results that take us to where we want to be. So earlier we saw functions like x squared plus 5x plus 6 and 2x cubed plus 3x plus 4. So I want to be able to work with relatively complicated functions, but to prove that f is big O of g straight from the definition would be hard, and we're going to see a result later that would make it easier. So you need some intermediate results, and I'm going to state the results, and the proof is on the slides, but I'm not going to go through the proof. So if f is big O of g and you have a constant lowercase a, for example, 5 or 7 or 14, it's got to be a positive number, 5 or 7 or 14, then a times f is also big O of g. Okay, so if you have, for example, x squared is big O of x to the fourth, then 5x squared is big O of x to the fourth. So that's multiplying by a scalar. This is adding. The two of these together make it a vector space. But anyway, this is adding. So if you have f is big O of g, f naught is big O of g naught, and f1 is big O of g1, then the sum is big O of g, where g is the maximum of the two little g's. In particular, if you have a g where both f naught and f1 are big O of g, then f naught plus f1 is also big O of g. And then finally, so I did scalar, I did addition, so there must be a multiplication one. And sure enough, if f naught is big O of g naught and f1 is big O of g1, then f naught f1 is big O of g naught g1. So it has a lot of awfully nice algebraic properties. And again, I put the proof on the slide so that a person can look at it at their leisure, but I'm going to pass over that in favor of doing an example that's more like the homework. That result, the result we just talked about, that I skipped the proof on, gives two principles for simplifying the big O expressions. I spelled expressions with 3 S's, I guess. So first, if a function is a sum of terms, of which one term has the largest growth rate, then we can omit the other terms. So you can think in terms of dominant term. Which of these, if you have a bunch of things added together, which of these is the dominant term? And second, if a function is a product of things, then we can drop constants. That is, factors that don't depend on the input. So if a function has a constant, say 7x squared, you can drop the 7. So here, for example, is f of x is 5x cubed minus 3x squared plus 12x. So there's 3 terms there, the 5x cubed, the minus 3x squared, and the 12x. Of the 3 terms, the one with the largest growth rate is 5x cubed. And now, we haven't actually seen the result for that. We're going to see it very soon. But isn't that intuitively clear? 5x cubed grows faster than, say, 12x. Isn't that intuitively clear? So by the second result on the prior slide, not the proof slide, of course, but the slide before that, then because this term is clearly big O of 5x cubed, this term is big O of 5x cubed, and this term is big O of 5x cubed, we can drop all the terms except for the big O, except for the 5x cubed. Similarly, because 5x cubed has a constant, 5, you can drop the 5. So we get that this f right here, 5x cubed minus 3x squared plus 12x, is big O of x cubed. And obviously this is a simplification over this. Okay, the second definition that we have is that we've already expressed big O. We've already used big O to express that the growth rate is less than or equal to. If f is big O of g, then the growth rate of f is less than or equal to the growth rate of g. And now I want to give us a way to express the growth rate equal. So that's big theta. We say that f is big theta of g if both f is big O of g and g is big O of f. So that is to say f is pinched between these two constant times g's. But the point is that the growth rates are equivalent. Not equal maybe, but equivalent. So if you had 7x cubed and 5x cubed, those two functions would be, you would say that 7x cubed is big theta of 5x cubed. Here's the picture. This is the right picture to have. Inside of the rectangles are all the functions that we'll be concerned with. You see here this light green triangle, not the dark green, the light green triangle. All of those functions are big O of n cubed. That's what this says. All the functions inside the bigger triangle are big O of n cubed, including, for example, the function n squared. So the dark green triangle is all the functions that are big O of n squared. Well, if you're big O of n squared, you're also big O of n cubed. If your growth rate is less than or equal to n squareds, then your growth rate is definitely less than or equal to n cubed. What about the or equal to? Well, there it is at the top. See, the big triangle is big O of n cubed, and there at the top is a tiny little section that consists of all the functions whose growth rate is essentially equal to, is equivalent to, n cubed. So I drew that as a little circle. And likewise, at the top of the triangle for big O of n squared is a little circle of containing all the functions whose growth rate is pretty much equivalent to n squared. Okay, so big O of n cubed is really a set. Big O of n squared is a set. It's a set of functions that have a growth rate less than or equal to n cubed or n squared, whatever you look at it. Okay, now we're ready for what I characterized earlier as a shortcut. So we're going to use calculus to give us, to enable us to rapidly do these calculations so that you're not, in most cases, having to pick the capital N and the capital C and then go through a sometimes difficult verification. So it goes like this. If you want to compare two functions f of x and g of x in ratio, You take the limit as x goes to infinity, and we saw why you take the limit as x goes to infinity, because you have to ignore some initial nonsense. And you figure out what is that limit. And for the kinds of examples that we look at, we'll be able to figure it out. There are three cases. The limit could be 0, the limit could be between 0 and infinity, or the limit could be infinity. So if the limit is 0, if f over g goes to 0 as x goes to infinity, then f is big O of g, but it's not the case that g is big O of f. That is to say, f is less than g in some sense. F is big O of g, but it's not the case that g is big O of f. If the limit is between 0 and infinity, I notice a typo here. That's not supposed to say less than or equal, it's supposed to say less than. I'll correct that before I upload it. If the limit is strictly between 0 and infinity, then both f is big O of g and also g is big O of f. If, for example, the limit is 2, we saw the example of a function that was 2x squared and another function that was x squared. So if you had a limit of 2, if the limit is between 0 and infinity, and again, I'm sorry, that's a typo. If the limit is strictly between 2 and infinity, between 0 and infinity, then the two of them have equivalent growth rates. That is to say, f is big theta of g, or you could say the exact same thing, g is big theta of f. And the last case, having covered the 0, the intermediate, the last case is L is infinity. If L is infinity, then the function on top is bigger than the function on bottom. So g is big O of f. G is grows at a rate less than or equal to f's growth rate. But it's not the case that f is big O of g. So g is sort of strictly less than f in growth rates. Okay, I'm cognizant that that folks are Googling around and seeing things in other places, so I try to make sure to cover those gaps if a person can feel like they saw it. So here we go. The first case in the prior slide, where the L is 0, where f's growth rate is strictly less than g's. That case is sometimes called little o. F is little o of g. And here's the sort of official definition that doesn't depend on the limit, because sometimes you'll run across where you can't apply the limit, no calculus function applies. But the point I'm going to make is just that if the limit is 0, that falls under this definition. So f is strictly less than g falls under this definition, a little o. And finally, a special case here is that f and g have a limit of 1. So f and g are in some sense in the limit the same. Of course, they're not equal, but they're somehow the same in the limit, and we call that asymptotically equivalent, right? F twiddle g. So there's a lot of notations flying around. I wrote it down here, sort of in terms descending. The ones down at the bottom are rarer than the ones up top. I'm mostly interested in the first two. The analogy is that f is in big O of g is like saying f's growth rate is less than or equal to g's. If you say f is in big theta of g, that's saying that f's growth rate is approximately equal to this, is equivalent to g's. Okay, so those first two are the main ones that I'm interested in, but you will see the other ones from time to time, especially little o. And again, I'm going to pass over the proof just by virtue of doing examples, that's all. And the examples that we're going to do is a person recognizes, I hope a person recognizes, the limit as x goes to infinity, f of x over g of x equals L, as appearing in L'Hopital's rule. I mean, that's one of the main reasons to cover L'Hopital's rules calculus for exactly this moment, because we need it right now. L'Hopital's rule, you remember, is that if you have to calculate the limit as x goes to infinity of f of x over g of x, and f goes to infinity and also g goes to infinity, then one thing you can try is to take the derivative of both functions and see if you can calculate that limit. Sometimes you can calculate that limit, and those two turn out to be equal. So, time for examples, but the good thing about this subject is that these examples prove to be very easy. That's why it's called a shortcut. So I'm going to consider again two functions here, n squared plus 5n plus 6, and 2n squared plus 3n plus 4, and I happen to put g on top. I could have put g on the bottom. The point is I'm comparing the two functions in a ratio. I'm going to apply L'Hopital's rule as a reminder of how L'Hopital's rule goes. So 2x squared plus 3x plus 4 derivative is 4x plus 3. And x squared plus 5x plus 6 derivative is 2x plus 5. I left out the plus 5. Sorry about that. and you get a limit of 2. So we get that f is big O of g, and I'll just remark that it's also the case that g is big O of f because 2 is strictly between 0 and infinity. So the two of them are the same order of growth. The two of them are big theta. Next example, 2x cubed, x squared. So we saw this example before. This is the one where one function races ahead of the other. So I happen to put that one on top. I could have put it on the bottom, but I happen to put it on top. 2x cubed plus 3x plus 4 compared to x squared plus 5x plus 6. When you apply L'Hopital's rule, you get 6x plus 3. When you apply L'Hopital's rule, you get 2x plus 5. That's the plus 5 I missed on the previous line. I'm sorry about that. You have to apply L'Hopital's rule again to get 12x and 2. And now 12x over 2 clearly has a limit of infinity because there's an x on top. So g is big O of f, but f is not big O of g. That is to say that the bottom is growth rate less than or equal to the top. But in fact, because the top is not less than or equal to the bottom, really the bottom is growth rate strictly less than the top. Basically because that's a square and that's a cube. Okay, so L'Hopital's rule enables us to make those conclusions, enables us to compare those functions very easily for the kinds of functions that a person routinely sees. And what that means is that we get a hierarchy. We were able to compare these functions in some reasonable way. And the hierarchy goes like this. These are the slow-growing functions. These are the fast-growing functions. The slowest growing function, we're looking at constant algorithms whose runtime growth is constant. You know, you might, for example, have a hash function. Algorithm whose runtime growth is constant. Algorithms whose runtime growth are logarithmic, or even algorithms whose runtime growth are linear, or even x log x. Those are all pretty usable algorithms, very fast algorithms. By the time you get into algorithms whose runtime growth is quadratic or cubic, you're starting to see a little bit of a slowdown. And by the time you get to algorithms whose runtime growth is 2 to the x, or 3 to the x, or, you know, God help us, x factorial, those are basically unusable. So these are slow-growing functions, these are fast-growing functions, and when you're measuring runtime, slow-growing is what you want. And just a remark, not every pair of functions can be compared. It is something of a mystery why most of the functions that a person runs across fit into that hierarchy, but strictly speaking, not every function does fit into the hierarchy. Okay, very good. So the basic idea, the sort of lesson for the homework is, if you can put it into a form to which you can apply L'Hopital's rule, then you can rapidly get an answer. Okay, very good.